Hey everyone, let's jump right into today's explainer. Get ready because we're looking at a truly fascinating 19th century engineering puzzle, one that literally changed how we understand and measure electricity. We're talking about a concept here that honestly feels a bit like magic, but it's grounded in pure, elegant logic. So here is the big question we're tackling today. How exactly do engineers measure a tiny, completely unknown electrical resistance and do it with perfect accuracy? Really think about that for a second. You know, when lives depend on the accuracy of a high-precision sensor or the integrity of a complex circuit, engineers absolutely do not just guess. No way. They need a flawless, rock-solid system to find that exact unknown value. Well, the answer to that mystery is something called the Wheatstone Bridge. It's this brilliant 19th century balancing act of a circuit designed from the ground up to measure that unknown resistance perfectly. Okay, let's dive into this and see exactly how this incredible piece of historical engineering actually pulls this off. Section 1. The Diamond Circuit Setup. Let's meet the cast. To really get the bridge, you gotta mentally frame its physical layout as a diamond shape. It's like a giant diamond puzzle. Let's break down the 4 key resistors in this setup step by step so we don't get overwhelmed. First up, we have resistor P and resistor Q. These guys are our anchors. We already know their exact values. Then we have resistor R. Now, this one is variable, meaning you literally have the power to turn a dial and change its resistance actively while you're working. And finally, the star of the show, resistor S. This is our target, the ultimate mystery resistor we're trying to figure out. Now, we drop the final, absolute most crucial component right into the very center of our mental diamond, the galvanometer, labeled G. Think of this galvanometer as our ultimate detector. It sits squarely across that middle wire, literally forming the bridge in our Wheatstone Bridge, just quietly waiting to detect even the tiniest flow of electrical current passing across the center. Moving on to Section 2, the magic of balance, the turning point. This is it. This is the exact turning point where a totally standard circuit transforms into a high-precision tool. Let's compare the two states. First, imagine the chaotic, unbalanced state. Electrical current is just surging through all the branches, totally spilling over into our center galvanometer. It's a mess. But then, contrast that with the balanced state. This right here perfectly illustrates the magic of the Wheatstone Bridge. In this balanced state, the electrical potentials at both ends of that galvanometer are exactly the same. And because there's absolutely zero difference in potential, zero current flows through the center wire. It is perfectly, completely calm. The needle hits 0. Now, what's really interesting here is that this isn't a dead circuit. I mean, electricity is absolutely still flowing like crazy through the outside diamond, but the needle hitting 0 in the middle, that's the exact moment the magic happens. It's telling us, hey, we've achieved perfect balance. Section 3, the physics exam hack, the math revealed. When we finally hit that 0 point, it unlocks a massive, game-changing shortcut. It's literally your ultimate exam hack. Here is the big payoff equation. P divided by Q equals R divided by S. So, the crucial point is that when that galvanometer needle drops to 0, the ratio of our known resistors is perfectly mathematically equal to the ratio of our variable and unknown resistors. It's just beautifully simple. Okay, let's walk through how you actually use this in practice. Step 1, you just adjust your variable resistor R, tweaking it to balance the bridge until that galvanometer reads exactly 0. Step 2, you set up your simple ratio, P over Q equals R over S. Step 3, basic cross multiplication. Since you already know the values of P, Q, and R, boom, you easily and accurately find the mystery resistor S without a single drop of guesswork. Section 4, real-world applications. Let's move to and see how this builds beyond the textbook. Now, you might be sitting there thinking, okay, sure, this is just a neat little math trick for passing a physics test. But actually, scratch that. It is so much more. This exact 19th century textbook logic, it's literally powering the high-precision sensors we rely on right now. When an engineer designs a high-precision pressure sensor, they use this. Modern strain gauges measuring tiny, microscopic deformations in bridges or airplane wings. Yep, they use this. Even the digital weighing scales in your bathroom or at the grocery store use this exact Wheatstone Bridge logic to detect microscopic changes in electrical resistance and give you a perfectly accurate weight. It's everywhere. The core principle has literally never changed. If you understand how this simple diamond circuit achieves perfect balance, you've unlocked the foundation of modern electrical measurement. Master the bridge, and you master the circuit. It takes this whole narrative of the mystery box from an impossible, frustrating puzzle into a deeply satisfying, empowering victory of pure logic. I really hope you enjoyed diving into this awesome slice of engineering history with me today. But, there's always more to learn. So I want to pose a question to you. Which Class 12 experiment should we break down next? Think about the concepts that totally stumped you, or the ones you find absolutely fascinating, and let me know. Thanks so much for joining me on this explainer, and I will catch you next time.